So my name's Jonathan, I work at CoreOS. As a bit of a disclosure, I don't actually work on the Kubernetes performance team at CoreOS, but they're all in SF and they weren't able to make it, so I'm just going to be talking kind of on their behalf. But I have been involved with this stuff a bit. And this also, the title of this talk is a little bit of a trick. Everyone loves 10x performance improvements. That sounds great. But actually, I want to use this as well to kind of argue a bit why metrics are important and why you should use more of them and use more of them with systems like Kubernetes. Okay, so first start with a little bit of, again, trying to kind of persuade you why metrics are important, why we should instrument everything, like the Prometheus guys keep telling us. And then the first, obviously the main two reasons that people often think about coming from DevOps or coming from older systems is the first is health monitoring, right? So that allows you to easily kind of measure how healthy your system is performing, whether at an individual service level or maybe at a higher level within kind of your stack. And then also to do different alerting based on that. And time series based alerting is obviously a bit more powerful than older kind of more sort of static systems like things like Nagios and stuff with simple checks. But kind of trying to move beyond that to seeing what other things that this new metrics kind of world allows us to do. Something that I think someone touched on in a talk earlier today was maybe, or I was also having a conversation with someone about it, is you can start to use metrics maybe for sort of business insight things. I mean, obviously people do use metrics for business insight, but even something like Prometheus, maybe if you're trying to capacity plan, you can get an idea from the kind of metrics that Prometheus can expose about what your utilization is like in your cluster and when you might start to need to think about getting more servers. Or similarly, you could even, if you wanted, track things like how users are interacting with your apps. Auto tuning is kind of a new area, I'd say. We're seeing this start to be explored in Kubernetes, for example. And the idea here is that once you have the system running, you want to be able to automatically adjust state. So maybe expand resource usage on the fly automatically in response to demand or in response to system performance. Your auto scaling on Kubernetes would be a good example of that. And metrics is really a key part to such a system. And then finally, the one I want to kind of focus on today is debugging with metrics, and this is also sort of touched on in the last talk as well. The idea here is just to see what once we start using metrics for monitoring and health alerting and stuff, but now we start to see what kind of things, other kind of bonuses it can provide, and how we can use it to kind of do debugging a bit better than kind of old style ways. So this is kind of a case study of how we used metrics and among other things to improve the Kubernetes scheduler performance. By a good factor. So in a way, this is a talk about how to use Prometheus, but it's also, as you'll see, it's a talk about how we didn't use Prometheus as we maybe we could have or should have, and how some things we kind of learned from that and sort of fed back into projects looking forward. So again, to set the context, we sort of set up, I think about a year ago, we set up a team at CoreOS focused on Kubernetes scalability. Since we do a lot with Kubernetes at CoreOS, we're big fans, and the idea of this team was that we want to make sure that Kubernetes can scale, really well, particularly compared to kind of competing sort of container scheduling systems out there. And the first step in being able to scale something is just kind of understanding the performance. So the first thing the first kind of task of this team was just testing Kubernetes and understanding how it performs, and start to kind of think about where maybe some of the bottlenecks are. For anyone who's not really familiar with Kubernetes architecture, this is at a very high level. You have sort of the central, in the middle you have the sort of scheduler, what we call the control plane. So that's the scheduler responsible for deciding where to put containers in the cluster, and the API server, which is your first port of entry for all your interactions with Kubernetes, and how Kubernetes sort of interacts internally. And then the backing store for all Kubernetes operations is currently is etcd. Generally that runs sort of separately from the control plane. And then finally, the bulk of kind of your cluster generally will be, your worker nodes or your kubelets. And those are pretty dumb, relatively speaking. Those are just getting work assigned to them and then actually running the containers. That's where, at the end of the day, your applications run. But most of kind of the special magic and logic in Kubernetes happens, arguably happens in the scheduler and the API server. So our initial focus in the Kubernetes scalability team is on this control plane. And that's because the worker nodes are relatively independent. Whereas the control plane is involved in everything in the cluster. So every time you schedule an application, every time an application needs to be rescheduled, or you want to scale up an application, that needs to go through the control plane. Whereas it's only going to touch relatively independent number of worker nodes. If a worker node, is performing badly in itself, that's only going to affect, the damage from that's kind of isolated. It's only going to affect the pods that are running on that node. So the first thing we did was use this tool called KubeMark, which was developed by the Kubernetes community. And the idea here is just to be able to, rather than having to spin up a 1,000 node cluster to be able to test stuff at scale, we want to be able to simulate the worker nodes. Excuse me. So we can test larger clusters and really focus on this control plane. And so the initial question that we focused on was how long does it take to run 30 pods on every single node in a cluster? So we started just with a 100 node cluster, so 3,000 pods. How long does that take to schedule? And then the first way that we started looking at this with the sort of the output from KubeMark was just kind of going through the KubeMark and seeing with time how many pods get created and how many are still pending and so on. So the initial results showed a pretty linear rate of pod creation, but what we thought seemed pretty slow, like 20 pods a second. There was no delay between the pod kind of being created, being submitted to the schedule and being created, and then the delay between it being actually running on the system. That's the dotted line just under here. So it's very quick for a pod once it's been created to actually get to be running. So we suspected that this is probably a place to start looking at performance. It seemed like a bottleneck, so a place we wanted to kind of start investigating. So the first place to start, it's pretty stupid, but it's always the kind of the easy place to start looking is hey, if I've got a performance problem, if something seems slow, maybe I'm just using too many resources. Maybe the hardware's tapping out the hardware. Easy way to kind of jump in and look at that was using htop or top. But to see how the Kubernetes scheduler components, the control plane components are doing. So fired up top, and we see some reasonable CPU usage, but nothing extreme. We weren't seeing we had 16 cores. Most of them are still mostly sitting idle. Nothing too outrageous. Incidentally, so we could rule out hardware resource starvation as kind of the cause in this case. And I'll come back to you might be wondering why I'm using top. I'll come back to that a bit later on. So this suggests, again, the bottleneck's somewhere in the software that we're working with, in the control plane. But Kubernetes is a huge code base. It's quite complex. Finding bottlenecks in such complex code is never really trivial. So how do we know where to start? Well, this is where Prometheus came in for us. Fortunately, with all these Kubernetes API calls, Kubernetes actually already exposed metrics that sort of provided some information around latency and response time and stuff around these API calls. So we could start to look at those metrics to get a clue for where to kind of dig in further. So we reran the KubeMark suite again, and this time keeping a closer eye on, or actually looking at the metrics, monitoring the scheduler's metrics in particular. And it wasn't great, but it also didn't seem to be the culprit, because the scheduler's latency was only 7 milliseconds, which meant it could schedule about 140 pods a second, which was a lot better than what we were seeing. So this suggested the schedule is not actually the place to start, not the primary bottleneck. So the next step was actually involved looking at some other metrics, and unfortunately sort of adding different logs and print statements and things, partly because we didn't have enough exposed metrics at this stage. So the reason that the way that we found the first bottleneck really was actually adding more log debugging. And through this, kind of isolated contention to the replication controller, which is responsible for spinning up, the different replicas of a pod. There was some pretty low-hanging fruit in the replication controller, so that was an easy place to start. There were a couple of actually rate limiters in the client code, because I guess someone who had first written the code had said, oh, we don't want to overwhelm the API, and so removing those gave a bit of a gain. And then there was a little inefficient code path that was a kind of a quick fix, and it's kind of ironically the code path that ended up having quite a significant impact was a very, very simple thing. It was metrics registration. And just the simple fact of doing this metrics registration, in every request rather than registering once and allowing the operation to cache itself, actually ended up having quite a big impact on scheduling performance. So metrics aren't always great, but it did help a lot. We went, with that same 100-node cluster scenario, we managed to go from 20 pods a second up to over 300 pods a second. So that really seemed like a great start. Ideally, that would be the end of the story, but that's just kind of showing the improvement, initial improvement in the rate. As you can see, it's still kind of quite linear over time, but much higher throughput. So then we wanted to take it up to the next step from a 100-node cluster and move to a 1,000-node cluster. In this case, we weren't so lucky. The performance deteriorated pretty dramatically. We ended up going to a total kind of pod throughput of getting a pod running of just 5 a second, which was kind of worse than when we started. And actually, the rate of creating the pods was quite good, creating the pod entities, but actually getting them running, getting them replicated out there, remained quite slow. So you can see here, like on the sort of line on the left, is them being created, so that's happening quite fast. But in getting them actually running was slow, and sort of the latency there was deteriorating. This is the point at which the scheduler component started to become more suspicious, because the latency started quite high. If you remember when we started, it was down at, I think it was 7 milliseconds. Now it's kind of up to 60. And then over time, as the cluster grew, or as the number of scheduled pods grew in the cluster, the latency was deteriorating even worse. So, the metrics helped here, helped focus on the scheduler. So we felt we kind of isolated the next problem there. But again, like even within the scheduler, it's quite a complex code base. And we kind of reached a point where we needed to dive in more, in much more detail. The other problem that we had there was that kubemark, I mentioned this was taking 5,000 seconds. So kubemark runs were taking a couple of hours each test. So it's really a little bit too slow to kind of practically be able to debug this more quickly. So in the end, what we ended up doing was kind of creating this sort of lightweight version of the benchmarking tool that there's more details in the link in the slides. To be able to simulate this more quickly and then kind of boil it down to the fundamental contentious bit, boil it down to a Go unit test that we could run repeatedly very quickly and analyze the performance there and trying to analyze the slow performing parts of that. After a bunch of Go profiling and kind of graphing it out and diving into it in more detail, actually isolated a few performance hotspots. This is as one example. Ended up that actually most of the time that the scheduler was spending was just doing this rounding operation on a number, on a value that was buried away somewhere in the Kubernetes code base. So spent some time working on little fixes to those. A lot of them ended up being very, very simple actually. I'm just optimizing some of these things. Put up a number of pull requests to Kubernetes. Most of them got merged, and it was very successful in the end. We ended up, the average scheduling latency dropped pretty significantly, but even more significantly, the sort of total time of scheduling, being able to schedule 30,000 pods into 1,000 nodes, dropped. This is the magical 10x from 80 seconds down to just 587 seconds. And all this was achieved through a pretty small amount of code in the end. Just 4 pull requests, none of them particularly significant. Some sort of minor fixes that could really brought a lot of benefit. And this is kind of through a combination of tools. We use Prometheus a bit to kind of help us guide us in the right direction. But then when we needed more detail, we would dive into things like pprof, using pprof to analyze the Go runtime's performance. We sort of had our own plotting thing, which I'll touch on in a second, and using top to look at the system metrics. So all in all, it was a pretty good result. But I want to talk a little bit more about like what we didn't really do right and how we could have done better, and just in terms of how we went through this process. We really didn't use metrics in Prometheus in the way that Prometheus kind of thinks about them as much as we could have. So, for example, the first kind of obvious thing was like jumping onto a machine and using top. This is not really a production way of analyzing performance. Instead, it would have been better to expose this. I mean, hopefully this is already exposed in your Prometheus environment, but to be able to analyze system level metrics, with something like Prometheus over time. Similarly, with this, the kubemark test, we were actually doing a lot of kind of log scraping and ended up generating these graphs that I've been showing. They're kind of this custom graphing tool that was created for this. But really, it'd be better to expose this stuff directly and take advantage of all the stuff that you already get in like the Prometheus ecosystem. Like we could graph this stuff with Grafana and do more advanced kind of queries and analysis with PromQL. So even though Prometheus helped us in this exercise, we definitely didn't use it, I would say, as we should have, or as much as we should have. And subsequently, after this experience, we've been in the process of adding a lot more metrics to some of our own services like etcd, particularly in the new etcd v3 API, and then in the v3 store, and then also in Kubernetes itself. So why are metrics better? Why have I said those things are wrong? Couple of quick reasons to kind of, I guess, reiterate. It simplifies the lower level analysis because you can start to extract information about your code, how it's running, without actually having to dive into the code and add print statements and stare at particular things. You can really get interesting information and be able to point to a pretty specific area if you instrument thoughtfully, while you're writing the code. Maybe just as important, there's no need to necessarily reproduce the problem. So rather than having to add debug statements and then go through it again and make sure it happens again, if you have a sort of metric setup, you're already collecting this information. It's already there, so you already, at the time that the problem occurred, or the initial time that you produced this poor performance, you should be able to go and already get that information. You don't need to recompile your code or attach a live debugger, which obviously has its own effects on performance and code and runtime and such. And then you get this nice dynamic power of the PromQL language, for example, and the different graphing ways you can interact with it. You don't have these sort of things we result from with pprof, like these SVG graphs we sort of looked at earlier. And then that's kind of at the lower level of debugging, but then at the higher level you get these all these really nice features that kind of stepping back and try to analyze performance at a higher level. You get being able to look at things across a fleet, so seeing about how maybe different versions of your software are performing across the cluster or in different scenarios, different hardware platforms, for example. You can aggregate information from many different, for example, many different runs of a particular piece of software. You have that history. Provided you're keeping history, so you can kind of look back and compare with different scenarios. And then maybe one of the more important things as well, particularly in distributed systems, is you can see correlations more easily. Correlations between different metrics within the same piece of software, or maybe within different components. So a scheduler metric, in the case of this Kubernetes control plane, correlating with some API metrics exposed by the API server. So yeah, I think metrics are great. We should use more of them, and we think you should use more of them. They don't provide all the answers. At the end of the day, even if we had instrumented this stuff much more thoroughly from the beginning, we would still probably need, at the end of the day, we would still need to dive in to find out some of these problems. Like some of the issues that we ended up finding, where it comes down to a simple, a maths function, the implementation of a particular maths function. Realistically, you're probably not going to be instrumenting every single call like that. It's just not practical. And it doesn't necessarily help you in finding those really critical hotspots. But it really gives you a good starting point for where to start looking. And that's part of the reason why it was so helpful to us in this process. Approaching a really big, complex project like Kubernetes, a distributed system with these different moving parts, and wanting to answer these have these sort of high-level questions of how can we improve performance for the system as a whole. Metrics are really critical to help point us in the right direction. That's pretty much my talk, but we love Prometheus, and I just wanted a quick shout out if anyone's interested in working on Prometheus 2. We're hiring in Berlin, so feel free to talk to me or anyone on the team. And thank you.
So, questions? No questions? Okay, that's a first. Right. I'm very disappointed in you. Okay, well, there's a question. I'm no longer disappointed in you. I'm now disappointed in everyone except me.
Have you noticed the lack of metrics in Kubernetes, and have you started to contribute more metric instrumentation back? And
yeah, we definitely have. Fabian and Frederick would be a better place to talk about specifics, because they've actually put up some PRs in the last few weeks about. Frederick, do you want to talk to that? Yes.
We actually started the special interest group in Kubernetes, SIG instrumentation, which has a meeting today, where we discuss which kind of metrics make sense to instrument within Kubernetes, and basically anyone interested in that can join and pitch in.
Yeah, if anyone is interested in Kubernetes metrics, there will be the first meeting at 6:30 today. So we will stay here and just join the video call. So if you want to join, but yeah, you will get free drinks otherwise.
So to be clear, your choice is either to go to the monitoring SIG, where where CoreOS people will be present, or go to the beers sponsored by CoreOS. So they've got you both ways.
So another question, just a remark. Prometheus metrics exposed by Prometheus itself, they are not great in a way. We have issues in GitHub to fix them, but they are often driven by exactly what you did or should have done. We were coding Prometheus and wanted to optimize it, and then we had the metrics we needed right now. That's also like we always use pprof, of course, as well. But the combination, like pprof is always the snapshot, you mentioned that. And for example, like chunk ops, to like connect this to my talk where you could see what is actually happening with the chunks and then just get a graph over like the last day, what has my Prometheus server done when. It's really great to like know where the bottlenecks are and where your resources are burned.
Another interesting thing I find, because I'm always telling people that all these tools are complementary. Like you need your metrics to, as you said, figure out where to start looking. You need your logs then, your profiling tools, your debuggers, your dtrace to then dig into the detail. There's lots of people talking about, can I have one dashboard or one system that'll do all of this for me? Yeah, let me know if anyone finds one. Okay, so at this point we are at, let's see, have an hour break.